Hi, everybody. So, I am lecturer in mathematics from Giraj Government College, Nizamabad. Today topic is in mathematics, BSC third year. So, null space and linear transformation. So, now the definition of null space. Definition of null space is A is M by N matrix, the set of all solutions of the homogeneous equation Ax equal to 0 bar. So is called null space of matrix A. It is denoted by null A. So null A definition x such that x is in R to the power n and Ax equal to 0 bar. So this Ax equal to 0 bar so is x equals 0 bar is also called homogeneous equation. So the vector x we find from the equation x equal to 0 bar, then x is called null space of the matrix A. And this null A is subspace of A to the power n. Null A is subspace of R to the power n. So null A definition set of all solutions of the homogeneous equation Ax equal to 0 bar. So here is M by N matrix and null space is subspace of R to the power n. Number of order of matrix is rows by columns. Null space is subspace of R to the power n. So null A equal to x such that x is in R to the power n and Ax equal to 0 bar. So here Ax equal to 0 bar, then we say that x is element of null A. So here we check let A be the matrix in uh, let A value is 1 minus 3 minus 2 minus 5 9 1 and U equal to 5 3 minus 2. So determine if U belongs to the null space of A or not. So when we say that U is element of null A, if AU equal to 0 bar, then U is called element of null A. So here we find AU value, A into U value. So product matrix is we get 0. So 0 0 means it is 0 matrix. So AU equal to 0 bar. Therefore we say that U is in null A. So next one example. So here W is given, W is and A value also given. We find AW value. So here AW equal to 0. AW equal to 0. So therefore we say that W is null A. W is in null A. So next same model, third example. So here one theorem is there. So the theorem statement is the null space of M by N matrix A is subspace of R to the power n. So here null space of an M by N matrix of A is subspace of R to the power n. So R to the power n means number of columns. So m rows and n columns here. So null space is subspace of number of columns of matrix, that is R to the power n. So here null space means x such that Ax equal to 0 bar. So if Ax equal to 0 bar, then we say that x is element of null A. So here we define first null A. So null A equal to x such that Ax equal to 0 bar. So suppose x value is 0, A into 0 bar equal to 0 bar. So we say that 0 bar is in null A. So what is subspace definition? Subspace definition is a non-empty set satisfies three conditions. First, zero element is belongs to H and U plus V belongs to H for all U comma V belongs to H and AU belongs to H for all A belongs to F comma U belongs to H. So these three conditions satisfied, then we say that H is subspace of the vector space V. So here first 0 is U is an element of null A. Next we will take U comma VB two elements in null A. So then AU 0 bar and AV also 0 bar. So now A into U plus V value, A into U plus V value, AU plus AV. So we know AU 0 and AV also 0. So that equal to 0. So A into U plus V equal to 0 bar. Then we say that U plus V is element of null A. So it is second condition of subspace. So third condition, if C is any scalar and we find the value ACU, ACU equal to C into AU value 0, C into 0 bar equal to 0 bar. So A into CU value also we get 0 bar. So therefore we say that. So here null A satisfies three conditions. One is 0 bar belongs to null A. Second one, U plus V belongs to null A. Third one, CU belongs to null A. So any non-empty set satisfies these three conditions, then we say that it is subspace. So now therefore we say that null A is subspace of R to the power n. So now here one more problem. So problems are there. So first W equal to ABC such that A minus 3B minus C equal to 0. So show in two different ways. W is subspace of R3. So subspace conditions are here there. One is the definition. So the definition, non-empty set satisfies zero element in that set. U plus V belongs to that set. Cu belongs to that set. These three conditions satisfied, then we say that that set is subspace of the vector space. One condition. Second condition is, so elements of W are span of the set, elements of W express span of the vectors, then we know span is a subspace. So by this theorem also we say that it is subspace. So in the now the definition, null space definition. So AU equal to 0 bar, then U is element of null A, and we know that null A is subspace. So here three conditions. One is the definition, one is the span, another one is the null space. So in these three, any one condition satisfied, then we say that that non-empty set is subspace. So here want two different ways. So one is the first here one condition is given, elements of W are ABC form, and condition A minus 3B minus C equal to 0. So from this we write A equal to 3B plus C, A equal to 3B plus C. So here A plus here ABC column or ABC row also we write. So A plus we write 3B plus C, B comma C. So here how many constants are there? B comma C are real numbers. So here B comma C are real numbers. B values we write. B values B into 310 plus C into 101 such that B comma C belongs to R. Means here we say that W is span of two vectors 310 and 101. Say these two values are U comma V. So W equal to span of U comma V, and we know span set is subspace. So therefore we say that W is subspace of R3. So it is the one type of definition of subspace. So now another one. So another one is A minus 3B minus C equal to 0 given equation. This equation we write in matrix form. So what is the form? 1 minus 3 minus 1 into ABC equal to 0 bar. Here A into U equal to 0 bar. So we say that ABC element is element of null A, and we know null A is subspace. So therefore we say that W is subspace of R3. So now next problem. So here let H be the set of all vectors in R4. So where A, B, C, D satisfies the equation A minus 2B plus 5C equal to D and C minus A equal to B. So here show that H is subspace of R to the power 4. So we write first equations, given equations, A minus 2B plus 5C minus D equals 0. Second equation, minus A minus B plus C equal to 0. So these two equations we write in matrix form. So what is the matrix form? 1 minus 2b 1 minus 2 5 minus 1 first row. Second row minus 1 minus 1 1 0 into ABCD equal to right side value is 0. So here it is A into U equal to 0 bar form. So U is, that is ABCD is element of R to the power 4. So we say that H is subspace of R to the power 4. So now next problem. So find a spanning set for null space of the matrix A. So here A matrix is given. So we want X, spanning set is X. So this A matrix is, so we find x from the equation Ax equal to 0 bar, means the matrix A is reduced to, upper triangular form. That form is called echelon form, using matrix row operations, and if we get the upper triangular form, so then again we write the equation Ax equal to 0 bar. In A, how many columns are there? We will take number of variables in the X. Suppose A have 5 columns. So here we take X matrix is x1, x2, x3, x4, x5 column matrix. So here first matrix A is reduced to upper triangular form. So reduced to upper triangular form means, so we make below diagonal elements are zeros. So for this, so in the matrix we make first row first element is 1. So by using that one we make below elements are zeros. So next we make second row second element 1. So by using that one we make below elements are zeros. Next we make third row element is 1, and we make by using that one we make below elements are zeros. So in this way, if we get the upper triangular form, that is in the matrix below diagonal elements are zeros, then that form is called upper triangular form. So here we get the upper triangular form. Again we write the equation Ax equal to 0 bar, A matrix and A into X matrix we equate to 0 equations. So we know the we get the equations in x1, x2, so on. So here listen first. So here we make matrix A is reduced to upper triangular form. So first we want first row first element is 1. So here minus 3 is there. So we want 1, means in the second row 1 is there. So we interchange the R1 and R2. First and second rows we interchange. Then we obtain 1 minus 2, 2, 3 minus 1 minus 3. So here 1 is there. By using this one we make minus 3 and two elements are zeros. So here the operations R2 is minus 3 plus 3 R1. So here 2 is there, 2 minus 2 R1. So 2 minus 2 R1. So now here we get the matrix 1 minus 2, 2, 3, so on matrix. Next we want second row second element. Second row second element is 0 there. So here we want third row third element. So here we interchange the rows. So we interchange the rows. Then here second row third element is 1. So by using this one we make below elements are zeros. Then we obtain the matrix here. So 1 minus 2, 2, 3 minus 1 first row. Second row 0, 0, 1, 2 minus 2. And third row elements are zeros. So here 0. So here diagonal. So it is the diagonal. So below diagonal elements are zeros. It is the diagonal. So below diagonal elements are zeros. So we say that it is upper triangular form of the matrix. Upper triangular form of the matrix. So now again we write. So now we write the equations from Ax equal to 0. It is the A. And what is X? X is x1, x2. This one is the X. X1, x2, x3, x4, xy. 5 columns are there in matrix A. So we will take 5 variables. So Ax into 0 bar, then we get the equations x1 minus 2x2 minus x4 plus 3xy equal to 0. X3, here it is the x3 plus 2x4 minus 2x5 equal to 0 bar. So in the third row all elements are zeros. Here we get two equations. These two equations we write. One is for x1 value, another one is x3 value. So these two values we substitute in the x vector. What is x vector? X1, x2, x3, x4, x5 is the x vector. Here we write the values. So how many variables are there here? Three variables are there. One is x2, another one is x4, another one is x5. We write x2 into its coefficient plus x4 into its coefficient plus x5 into its coefficients. So here it is the linear combination of the three vectors, say u, v, w. So therefore we say that, so these three vectors form null space of A. So elements of null space. So these three vectors are elements of null space. So it is the problem solution. So now next problem is, find a spanning set for null space of the following matrices. Same in the previous model. So first here matrix A. So this matrix A is reduced to upper triangular form. Again we write equations. Those equations are solved for x1, x2, so on variables. So with these variables we take from number of columns from the given matrix A. So here first solution, matrix A is reduced to upper triangular form, then we obtain 1 0 minus 7 6 and 0 1 4 minus 2 into how many columns are there in the matrix A? 4 columns are there, so we will take 4 variables x1, x2, x3, x4. We write first equation, x1 plus 0 x2 minus 7 x3 minus 6 x4 equal to 0. So next second equation, 0 x1 plus x2 plus 4 x3 minus 2 x4. So these two equations we write for x1, x2 values. These two values we substitute in the x matrix, x vector. So here it is the linear combination of two vectors, 7 minus 4 1 0 minus 6 2 0 1. So these two vectors form elements of spanning set. So it is the example. So same way fourth problem and fifth problem. So now column space of matrix. So column space of matrix is the column space of matrix of M by N matrix capital A is the set of all linear combination of elements of column A. So if A has columns A1, A2, so on An, so these columns linear combinations set is called column space of A. Column space, or it is denoted by col A, COL A, COL A. So now also defined as, so a vector x, find from the equation a vector x, find from the equation Ax equal to B, Ax equal to B. Then X is called element of column space. X is called element of column space. So here column space definition is span of columns of matrix A, set of all span of columns of matrix A, that is set of all linear combinations of columns of A. So column A equal to span of A1, A2, so on An. Another one definition, column A equal to B such that Ax equal to B for some x is in R to the power n. So here column space is subspace of R to the power n. So in the null space is subspace of R to the power n. Column space is subspace of R to the power m rows. So m rows and n columns are there. Column space is subspace of rows and null space is subspace of columns. So here the just opposite way. So here the problem. So find a find a matrix A such that W equal to column A. So from this definition we find a matrix A. So matrix A definition is linear combination of, matrix A means column A definition. So linear combination of elements of columns of matrix. So now W is given. So 6A minus B, first row, second row A plus B, third row minus 7B. So here two variables are there, A comma B. We write A coefficients. So A into 6 1 minus 7 plus B into minus 1 1 0. So here A comma B are linear combinations of the vectors 6 1 minus 7 minus 1 1 0. So these two are, we say that spanning set elements. So these two elements form a matrix A. So these two elements form a matrix A. So now A matrix is 6 minus 1. So 1 1 minus 1 0. So this way we find matrix A such that W equal to column A is given. So same way we find next problem. So here next problem is the so R 2s plus t r minus s plus 2t 3r plus s 2r minus s minus t. So here three variables are there r s t, r into its coefficients plus s into its coefficients plus t into its coefficients. So here so these three coefficients vectors form so element vectors form matrix A. So now the matrix A is so 0 2 3 1 1 minus 2 4 1 0 3 minus 1 minus 1. So next problem. So if A equal to 2 4 minus 2 1, so my second row minus 2 minus 5 7 3, this way is given. So if the what is the problem is, so if the column space of A is subspace of R to the power k, what is k value? So second one problem, if the null space of A is subspace of R to the power k, what is k? So here A matrix order. So A matrix is m by n matrix. Then column A subspace of number of rows, null A subspace of number of columns. So here how many rows are there? 3 rows are there. So first one answer is 3. So how many columns are there? 4 columns are there. So 1, 2, 3, 4. So second one null space of here in second one answer is 4. So here the columns of A each have 3 entries. Column A is subspace of R3. So k equal to 3. So where x such that x is defined uh, must have 4 entries. So null A is subspace of R to the power 4. So therefore k equal to 4. Same way similar problems are there in the first 17. So 17, so here it is 4 rows and 2 columns are there. So rows are column space subspace of rows, null space subspace of columns. So now rows, 4 rows are there. So column value 4. So null space subspace of columns. So null space value 2, number of vectors 2. So here matrix order is rows by columns. So 4 rows are there, 3 columns are there. Column A is 4 and null A is 3. So here 5 columns are there, 2 rows are there. So column A 2 and null A 5. So here 1 row and 5 columns. So row means column elements, column vector 1 and null space vectors are 5. So this way we find elements of null A and column A. So now the problem is find a non-zero vector in column A and non-zero vector in null A. So non-zero vector in column A means in the matrix A, every non-zero column is element of column A. So 2 minus 2 3, 4 minus 5 7, or minus 2 7 minus 8, or 1 3 6. These 4 columns are non-zero columns, and in these 4 any one vector is element of column A. So these 4 vectors also column A vectors. So we want a non-zero vector in null A. Non-zero vector in null A. So what is definition of null A? Ax equal to 0 bar, then x equal to 0 bar, then x is element of null A. So here A is given. So this A reduced to upper triangular form, and again we write equations from Ax equals 0. So those equations are solved for x1, x2, so on variables. So here how many in the A, how many columns are there? 4 columns are there. So here in the x vector we have 4 ordinates. x1, x2, x3, x4. So here from this AU equal to 0 bar, A is reduced to upper triangular form. We write equations x1 plus 0 x2 plus 9 x3 plus 0 equal to 0. So second 0 plus x2 minus 5 x3 plus 0 plus 0. So in the last x4 equal to 0. So x1 minus 9x3 equal to x1 plus 9x3 equal to 0, first equation. Second one x2 minus 5x3 equal to 0. Third one x4 equal to 0. So these four values we write in the matrix x vector x. So and values are common, then we get x is minus 9 5 comma 1 comma 0. It is the element of null A. So same way we do the next problem similar. So here two columns are there, two columns, and A has four rows are there. So any non-zero column in matrix A is element of column space. So column space elements are either first column or second column. So next we find non-zero vector for null space. So null space, so we write Ax equal to 0 bar. Matrix A is reduced to upper triangular form, and we write equations. Those equations are solved for the variables x1, x2, so on. So here A has two columns. So here we have two variables in the vector x. So first matrix A is reduced to upper triangular form. Then we get the matrix is upper triangular form matrix 1 minus 3 0 0 0 0 0 0. So from this we write equations. So first equation x minus 3x2 equals 0. Second row elements 0, third row elements 0, fourth row elements 0. So we get only one equation x1 equal to 3x2. So this value we write in the x vector. So we get the matrix 3 1. So it is element of null A. So now next problem. So right with an u comma v is there. So determine if u is in null A, same model. So now next definition is linear transformation. So here this way we find column A vectors and null A vectors. Uh, okay, next definition is linear transformation. So linear transformation means it is the mapping. So it is similar to homomorphism of groups. It is similar to homomorphism of the groups. So here the linear transformation definition is a linear transformation. So first here we have two vector spaces V comma WB, two vector spaces, and the mapping T from V to W satisfies the two conditions. Then we say that that mapping is called linear transformation. So first V comma W are two vector spaces, and the mapping T from V to W satisfies the conditions. First one, T of U plus V equal to T of U plus T of V. Second condition, T of Cu equal to C into T of U. So these two conditions are satisfied, then we say that the mapping T is linear transformation from V to W. T is linear transformation from V to W. So now, so next we define kernel of linear transformation. So kernel definition is, so first let T be a linear transformation from U to W. Then set of all T images of elements of U which are equal to 0 vector 0 W is called kernel of T. It is denoted by N of T. So we know already in the groups kernel definition. So here also same definition, T from U to W is a linear transformation. Then the set of all T images of elements of U which are equal to 0 vector, then this set elements is called kernel. So it is denoted by n of t. N of t equal to u belongs to u such that t of u equal to 0 w. So and n of t is subspace of w. N of t is subspace of w. So next definition is range of linear transformation. Range of linear transformation. So let T be a linear transformation from U to W. Then set of all T images of elements of U are called range of T, denoted by R of T, denoted by R of T. So here T from U to W is a linear transformation. Then set of all T images of elements of U is called range of the linear transformation. It is denoted by R of T. So here R of T set definition, T of U such that U is in U. So next we know that R of T, R here, R of T is subspace of W. So N of T is subspace of U. T from U to W is linear transformation. Then N of T is subspace of U and R of T is subspace of W. So here how we say that R of T is subspace of W means R of T satisfies three conditions of subspace. So three conditions are, first one, 0 bar belongs to R of T. Second, T of x plus y equal to T of x plus T of y. Next third condition, C T of Cx or Cx belongs to R of T. So these three conditions satisfied, then we say that R of T is subspace of W. So now here some problems are there. So the problems are, first, so T from P2 to R2 by T of P equal to P of 0, P of 1. T of P elements, T definition is T of P equal to P of 0, P of 1. If P of T equal to 3 plus 5T plus 7T square, then T of P value 315. So first show that T is linear transformation. T is linear transformation means we show that the mapping satisfies two conditions. One is T of P plus Q equal to T of P plus T of Q. Second one, T of Cp equal to C into T of P. So these two conditions satisfies, then we say that T is linear transformation. Means first we will take P comma QR, two polynomials of P2. P2 means it is second degree polynomials. P2 is set of all second degree polynomials. So P comma Q belongs to P2 and this P2 elements satisfies the condition T of P equal to P of 0, P of 1. So now T of P plus Q equal to P plus Q into 0 and P plus Q into Q of 1. So here P of 0 plus Q of 0, P of 1 plus Q of 1. So we write P values plus Q values. We say that T of P plus T of Q. First condition satisfied. Same way T of Cp. So C into T of P. So these two conditions satisfies, then we say that T is a linear transformation. So here second problem also there. So that second problem is, so find a polynomial P into P2 that spans the kernel T and range T. So this we want the polynomial such that it is the element of kernel T and range T. So kernel T means, so T of U equal to 0 bar, then U is element of kernel T. So here first, any quadric polynomial Q for Q of 0 equal to 0, Q of 1 Q of 1 equal to 0. It is the definition of kernel T. So kernel T means right side value 0 bar. So will be the kernel of T. So these two conditions satisfies in a matrix, then that matrix is element of kernel T. So q of 0 value 0 we want, q of 1 value 0 we want. So this way we define one polynomial. So we say that polynomial q of t equal to t into t minus 1. T into t minus 1 means this polynomial satisfies t value 0, then polynomial value 0, t value 1, then polynomial value 1. So it is this type polynomials are elements of kernel T. So next we find element of R2. R2 means here we want two variables x1, x2. So we define one polynomial x1 plus x2 minus x1 into R, p of 0 equal to x1, p of 1 equal to x2. Or this p of 0 equal to we say that x1, p of 1 equal to we say that x2. So these two polynomials are elements of range of T. So this way we find this way another similar problem is there. So here also same model. First case show that T is linear transformation. Second case find the elements of kernel T and range of T. So here the problem p of 0, p of 1. So same model, same problem is there. So here in the null set elements q of 0 0, q of 1 also 0. So satisfies this condition. So this is the problem. So we get why not to stop here. So the so this way we find null space and column space vectors and linear transformation. We find elements of range T and null kernel of linear transformation, kernel of linear transformation and range of T, and we find elements of null space and column space. So now, so thank you.